The topic of this lecture is modeling concepts. I'm going to start off talking about physical modeling, which you always do at the outset of the problem. Then we'll talk about finite element modeling, and I'll conclude with some sheet metal concepts. Today I've asked Dr. Don Dewhurst from the Ford Research Laboratories to stop by, and he'll cover the last two-thirds of the topics. Don's going to talk about element distortions. He's going to give an example in plane stress, show how the skewness of plate bending elements affects their accuracy, and he'll end with the story about solid elements where he shows an unusual locking behavior. Several years ago, I talked with Jerry Joseph from McNeil Schwindler Corporation, who was their customer relations expert. He handled all the incoming calls from people doing finite element work all over the country and using Nastran. But one of his observations was that half the calls had nothing to do with finite elements. They were purely questions about the physical model of the problem. In other words, is it a plate, or is it a solid, or is it a beam? What is it? And so I like to separate out what I call physical modeling from the finite element modeling. So when someone puts a component on your desk and says, I want an analysis done for this given problem, you have to go through some logic. You have to find out what kind of a structure is it. Is it plate-like or solid-like? Is it made of reasonable engineering materials, or is it something gushy and slushy that's going to be hard to characterize? What are the boundary conditions? Often boundary conditions are not either rigidly clamped or free, as we often assume in theory, but often it's some sort of intermediate elastic support. You might have to model the underlying earth or supporting structure out some distance to capture some of that elasticity. What are the loads? University students are always perplexed when they find in the real world that the loads are often not well defined. Aerospace companies, for instance, often have loads departments that are almost as big as the stress department. Not usually, but certainly defining loading is very important. How does the body deform? Is this going to be a classical kind of a torsion or a bending or extension? Anything you can deduce about the way the loads act on the body will help you model the body. How will the body fail? Is it going to break near a stress concentration? Is it going to fail in tension? Is this material brittle or ductile? And where will it fail? You'll need a more refined model near the point of failure, whereas in the safe regions, often you can afford to do more crude physical modeling. How can you document these critical areas that might fail? You have to plan ahead and think about the characterization of the failure mode. Fatigue, for instance, today, three-dimensional fatigue is an area that's quite difficult to characterize in general situations. And lastly, are there any special features? Do you have reflective planes, and do you have symmetric loading about that plane or anti-symmetric loading? Do you have end releases of beams where you have moment or force release? Is your body made of some composite material that's perhaps layered or fibrous? And then the material itself, is it isotropic or some general anisotropy? Now let's turn to finite element modeling, which is really the heart of this course. If you had to ask one question, it is, how can the steepest stress gradients be modeled? And this means that you're interested in areas where the stress is changing rapidly. This could happen near a stress concentration, for instance. Could be a hot spot in a structure in some sense, either thermally or mechanically. Well, figuring out how to get the best model of the steepest stress gradients involves a number of sub-questions here. What kind of elements should you use? And there's a definite choice between solid elements and then plate-like or shell-like elements and beams, trusses, and so on. How many elements do you want to use? You need a mesh that's refined to a certain point, but you don't want to be ridiculous. Many engineering problems would have a goal of 5% accuracy. So if you spend 10 times as much money and get 1% accuracy, your boss might not be happy with that. To save money, there are areas in the body where the mesh can be made coarse. Then the other areas of high stress gradient have to be areas of fine mesh, and that's somewhat of an art. It's been taken over to some extent by parameters read into automatic meshing programs where you can give the number of elements per side. But in the future, there will probably be built-in mesh quality indicators and then estimates of error given back to the user. It turns out we're not there yet, though, and we're all hoping for that day when we get more feedback, more diagnostic information out of our computer runs. Now, what special finite element tricks need to be used in your project? Will you need single point constraints? Well, almost always. Will you need multi-point constraints? Quite a bit, although many problems don't. Will you need rigid elements? Many problems involve R-bar elements, for instance. Finally, what kind of resources do you have available for your analysis? And you have to be realistic on this in terms of your own time, in terms of computer power, in terms of pre- and post-processing. And I've seen many young people make models that were too complicated for the situation at hand, and they basically became a burden on the institution where providing enough computer time became a real problem, and often the project was overrun in time and materials. So match your resources to the project at hand. In my career, several people have impressed on me the idea that an engineer should do a small, simple problem that characterizes the larger project and solve that thoroughly before plunging into the tough project. Both Professor Joe Isley at the University of Michigan and Louis Nagy at Ford Motor Company take that approach. So you should really consider making a small test run if you're using new element types, new kinds of loading, new solution sequences, anything that is a new challenge to you in solving your project. So if you can make some kind of a warm-up problem with only 2 or 3 elements, you often will arrive at the final answer quicker than if you hadn't done that small detour. An example in my consulting life was a 10-day project on the transient heat conduction in a truck disc brake, and I show the cross-section of it here. It's a body of revolution with the center line shown above. The disc itself is red hot, and there's a curious joint here which is bolted and which provides a resistance to the flow of heat. It's called a contact resistance. I'd never seen that before, and it turns out it's easier to model with a dissimilar model where you actually take a finite thickness heat conduction element and adjust the conductivity of the material to represent that surface contact resistance. So that was one new phenomenon for me, and the transient nature of the heat conduction was too. We actually tried to solve the full problem head-on and spent 2 days out of the 10 allowed spinning our wheels. The solver was new to me, and I was having trouble with transient heat conduction at the time. So I backed off and did a little 3-element model shown below, with one element representing the cast iron disc, another dissimilar model for the contact resistance, and then a wrought iron element for the hub of the brake. We spent fully 6 days working over this 3-element model until we thoroughly understood the process. And then we solved the full project in 1 day and got our results in on time. I'd like to give a few hints on sheet metal modeling. Sheet metal is a little more perverse than you'd think in the way that it can be joined and fastened together to form sheet metal structures. For instance, when you have spot welds in a lap joint, shown on the left here, if you are not careful, you'll get a continuous weld. For instance, if you join every overlapping set of nodes to each other, then if the element is a conforming element, you really have the effect of a fully joined or a welded structure. So if you really want intermediate openings to happen between the spot welds themselves, you have to have disjoint unconnected nodes on the two bodies that face each other such that they can pull apart. So you might, for instance, connect only every other node along that edge. Now for bolted connections, I did once a seat for an automotive supplier, and there were to be tests done to prove the theoretical analysis. And that was an eye-opener for me because Kurt Vail was the engineer who had once worked in sheet metal enough to develop a philosophy that you don't constrain all the rotations when you bolt sheet metal to something rigid. The fact that there's a hole and only a finite sized washer and so on means that you may not fully constrain the rotations. So Kurt's rule of thumb was when you bolt sheet metal structure down, only constrain the translational degrees of freedom. And I heard that and I laughed, ha ha ha, you know, boy, I'm smarter than that. So we built this model of the automobile seat and put on the government required loads at the center of gravity of the passenger in the seat and predicted our deflections. Then the test was done, and the test showed that the model was about 12% too stiff. And I thought, why is that? And of course models often are a little stiff because you don't model adequately all the holes and so on. But that was quite a bit. And so then I'd remembered Kurt's idea, and I went back and we released the moment constraint on the bolted points on this pan-like structure where it bolted to the more rigid rails, and made that only translationally connected and didn't constrain rotations. And then the answers were right on. They were only about 2% high. So maybe it's also a matter of introducing some flexibility in the structure to make up for the often too stiff finite elements that we use. In many companies, there's a lot of sheet metal work and then a lot of analysis of such structure. Normally, a plate is characterized by its middle surface. Unfortunately, when you do a lap joint of two sheet metal pieces, then the middle surfaces are separated by some distance, typically a plate thickness. Now, that's a bother, and it'd be nice if you could model, for instance, the mating surface of those two sheet metal pieces such that the two ultimate sets of elements appear to be a butt joint with no offset. At least one company that I know of, and it's a group in Ford, uses the concept of modeling mating surfaces throughout the body, and that is that they use an external surface of the sheet metal to characterize it rather than the middle surface. Now this means that about half the time when you join with a neighboring sheet of metal, you have a coincident surface that you're joining and no offsets are needed. Let me give such an example here, and it's contrived because I happen to have picked a body which has mating surfaces that form one continuous sheet surface shown below, which is in the shape of an H. Here you can see that the two pieces extending in the interior have a common mating surface. So you could get by then with your nodes lying precisely on this surface shown below. And then the same is true on the sidewall. Now, of course, if I bent one of these tabs up in the other direction, then you'd have a problem, because now your grid points would be separated conceivably by a plate thickness or even as much as 2 plate thicknesses. It turns out, though, that process, when carried out throughout the structure, will overestimate the stiffness of some components by 5 or 10% and underestimate others. So in general, it should cancel out.
Greetings, my name is Don Dewhurst, and I'm going to talk about some problems that we've done to illustrate some of the quirks or peculiarities of finite elements. Let's look first at a simple cantilever beam problem. Here's a cantilever beam that's been modeled with some nice rectangular elements. We've got the cantilever beam anchored at the left-hand side at the wall over there. A 1,000-pound tip load applied to the cantilever beam. We happen to be using MSC Nastran version 66, but the principle here I think is common to most finite element codes. The answer that we're getting for this particular model is that the peak deflection occurs over here and has a value of 0.0408. Now I'd like to contrast that with the very same beam, but next figure you're going to see is going to have 2 holes punched in the beam. So what we're going to show you next is the same cantilever beam, same mechanical properties, same material, same loads and boundary conditions, and let's take a look at the results. The load again is applied out here, the peak deflections at that point. Rather than being 0.0408, we're down to 0.0385. So that's a bit of a paradox if you think about it. We've actually removed material from the structure, and yet we've stiffened the structure. Now that represents a discretization error inherent in finite elements, and what the explanation is that either we have too much distortion in these elements that we've put in here this time, they're not perfectly square, or another way of stating that is that we have too few elements to capture the physics of the problem. The next slide is going to show a somewhat formal definition of element distortion. There are different measures of element distortion that one can make. And in fact, there are different definitions used by different codes. So you have to be a little bit sensitive to that. If we look at the figure, you'll see that the one common measure of distortion is simply an aspect ratio A over B, where one side's much longer than the other side. Another measure for the quadrilateral element is the skewness, shown here as an angle delta. Some codes use the complement of that angle over here as the measure of skewness. Then you can have an element that's tapered, let's say down to the right as shown here, with the ratio D over B, or you could have it tapered from bottom to top, or some combination of the two. So there are really 2 tapers, an aspect ratio, a skew in the plane, and then if you're dealing in 3 dimensions, you can also have a warp as shown at the bottom of the figure. Let's get back to the sketch of the problem that we showed originally. If we were going to improve that mesh to compensate for that error we had before, how would we change the mesh? If you look at the pattern, the mesh pattern that we have the things kind of circled around the hole. This plot shows the elastic strain energy due to that 1,000-pound load on the tip. As you know, the moment's increasing as you go toward the wall. Most of the strain energy is located over here in the beam. So if we were going to enrich this mesh to give a more nearly perfect solution, one way you might think of doing things is adding a row of elements across here. Perhaps a little better way to do that is, because all of the strain energy is located at the left, to put in another ring of elements around that hole. And indeed, if you do that, you get pretty good results for this problem. what we just saw was a plane stress problem. I'd like to show you another plane stress problem, and this time look a little more formally or systematically at the elements in the mesh and how they affect the answer. So let's look at a problem of a simple plate with a hole in it being pulled at both ends. So what we have is a long narrow plate, a central hole in the plate. We're pulling at the two ends with a known load, and what we have, of course, is the loads transmitted around the hole such that we get a stress concentration over at this end or this end of the hole. There's a lot of symmetry in this problem, so let's split the problem with a line down there and a line across there and look just at a quarter symmetric portion of the plate. So the first model we're going to try for this plate is we're at the upper left-hand corner, and we're going to apply 750 psi to the top edge in the vertical direction. We're going to channel the load through an area that's half the width of the plate. That is, the hole is taking out half of the area. And let's take a look at the finite element solution. So here's our quarter symmetric plate. We've got 3 elements along here, 3 along here, 3 along here. It's a pretty coarse model. Remember, we have the 750 psi at the top. We're going through half the area down here, so that's a nominal increase up to 1500 psi. And because the load has to flow around the hole, we've got it multiplied by some stress concentration. So our first solution is giving us 2330 psi for the answer to this problem. The next slide you're going to see is the same structure, but now instead of having just a few number of nodes or elements per edge, we're going to go up to 10 nodes per edge and take a look at the results. So here's the quarter symmetric plate again, same 750 psi load. Now you can see that the stress contours are a little smoother than they were before. That's a good sign. And our stress, instead of being 2330 as it was before, you can see now it's 3256. So the finer model has given us the higher stress. And that's kind of typical of these things. You tend to approach the correct stress from down below. That is, a coarse discretization tends to give you a bit too stiff of a structure. The next slide you're going to see is again the same structure, but now instead of having 10 nodes per side, we're going to go up to 20 nodes per side. And before, where we had 3256 psi as our answer, let's take a look this time. So here again, same structure, peak stress at the same place, but now instead of 3256, we're up to 3550. So we've gone from 10 nodes per side to 20 nodes per side. We've gone up still a substantial amount in the stress. So as far as we know, we haven't converged yet to the right answer for this problem. The last problem with the last slide we showed was 20 nodes per side. Let's try 30 nodes per side and see what happens to the answer. So here you see a stress of 3646 psi. You remember it was 3550 before, and we've jumped a bit in the number of elements. We've gone up 50% on a side. Take that and square it, we've got double the number of elements, and we're still getting some appreciable change in the stress. The last slide in this sequence, we're going to go up to 40 nodes per side, see what that does to the stress. And notice that when I go up from 30 to 40 nodes per side, the number of elements is the square of that ratio. So we're getting to a fairly fine model. The cost of the model, of course, is going to be somehow proportional to the number of nodes. Taking a look at this then, the quarter plate with the peak stress down here, we're getting 3693 psi. That's an increase of about 50 psi over the previous model. So we're still climbing a little bit, but we've come a long way since our 2330 psi in that first rather coarse representation. I'm going to change things a little bit now. We've been looking at a quadrilateral element. Let's change to a hexa element that is a three-dimensional element. But more important than that, rather than using the uniform spacing that we used before, let's consider kind of moving the nodes toward the place where the high stress is, that is using a non-uniform spacing of the elements. Take a look at the figure here. What you see is around the hole, these elements are a bit smaller than they were before, and as you get away from the hole, it's sort of a geometric progression from small to large. And if you look at the stress results on the right-hand side, we're all the way up to 3,807 psi. So what we're doing is getting, presumably, to the right answer much more quickly and more cheaply with this modeling. We're going to change gears a little bit here. We were looking previously at two problems that were plane problems or membrane problems. Now let's take a look at a plate structure that is a uniform plate and simply supported boundary conditions, uniform lateral load, and look at different amounts of skew and the effect of the skew on the results. If you take a look at this slide, again we have a plate bending problem, and we really have 5 different plates or 5 different structures that we're looking at. Some of them are 90 degrees in the corners all the way down to a 30-degree skewness as measured by this angle. And we're looking at coarse, medium, and fine meshes, that is 4 elements per side, 8 and 14 elements per side. What are shown here are quadrilaterals, but in addition to that, we're also going to look at the problem where we use triangles, and we split the short dimension of these quads to get the triangles. This problem was first, or at least I first became aware of it, in a publication by John Robinson called Finite Element News. This is referred to as the Morley skew plate problem because he came up with what are the right answers for these plates. So the problem we've posed is that of a plate with increasing skewness, 90 degrees, no skew, down to 30 degrees. And we're going to look at trias versus quadrilaterals, and we're going to look at 2 specific skewnesses on this next figure, that is the 80 degree and the 60 degree. Let's take a look at the figure. What we're plotting is percentage error and displacement, so the 0 error means that we've nailed the right answer. As we go down to these negative percentage errors and displacement, what we're getting is a stiffening of the plate. We're looking at, first of all, the 80 degree skewness, the quad versus the tria. So here's the line representing the quad. This is the fine model, this is the coarse model. Fine outperforming coarse as usual. Quad outperforming tria, and the relatively unskewed elements outperforming the relatively skewed elements. So 80 degrees is less air than the 60 degree skew. The next figure we're going to show is just a different representation of the data. This is going to have all of the data in it, and what I want to illustrate is a kind of a compensating effect, namely that if you have a lot of skewness, you can compensate for that by increasing the mesh density. Let's take a look at this figure. So here is air, percent air and displacement as a function of skewness and of mesh density. Again, percent air, the best answer is up here. The air is increasing as we increase the skew and as we decrease the number of elements per side. So what we have is a surface here which is good up at this region and worse where you have a coarse model with lots of skewness. We're going to look at a slightly different kind of problem now. This is going to be a 3D continuum problem rather than a membrane problem or a plate bending problem. We're going to look at a beam that's loaded at the 2 ends by equal and opposite moments. There's no shear on the problem. It's a rather severe problem in that we're going to model an entire beam by a single finite element. This is another one of those problems that was originally suggested by John Robinson through his magazine Finite Element News. He was challenging his readers to give results for this problem in a variety of codes, and then he compared the results of those codes in his magazine. Let's take a look at the figure. What you're looking at then is this beam-like structure loaded at this end by a moment, loaded at that end by a moment. Now there have to be some constraints here so that we don't have rigid body displacements, and since there are 6 rigid body displacements, we have to have 6 constraints. And you'll see that these constraints are thought out in such a way that we don't, for example, prevent this edge from shrinking due to the Poisson effect. So these effects, when you look at the reactions at these places, should be effectively 0, because I'm balancing this moment with an equal and opposite applied moment at the other end. And if our solution is correct, these things shouldn't really participate. Okay, so this is the problem that we're posing. Now let's take a look at some results. Let's take a look at this figure and see what the results are for a particular code, MSC Nastran. We've also run this problem in Abacus and some other codes. The results tend to be very similar. Here we have the figure repeated of the beam-like structure. Remember, we have the moment at the right-hand end, the balancing moment at the left-hand end, and we're pointing to this particular point because we're going to look at the displacements in all 3 directions, that is x, y, and z. So that's going to be a u displacement, a v displacement, and a lateral w displacement, which is the Poisson ratio effect along here. And you'll remember the original problem was posed up to an aspect ratio of simply 8 to 1. Since we went 8 to 1, 16 to 1, etc. with no change, we carried this out, and you'll see at something like 100 to 1 aspect ratio, we get our first flakiness in the results. That is, this lateral Poisson ratio deflection suddenly shoots off here as shown. However, the other 2 displacements, the u and the v displacements, continue to be good out until in the neighborhood of 8,000 to 1 aspect ratio. That problem worked out quite nicely with just a single element, but you'll remember that all of the angles in that element were at 90 degrees exactly. We wanted to explore what happens when those angles aren't so nearly perfect, so we introduced a second element, made 2 elements back to back to represent this uniform beam. And if you look at the picture, what you see is the same dimensions as before, the moments applied the same way, same constraints, but now we have this pair of elements, and we've purposely warped the interface between the 2 elements. Okay? And we tried this with a range of warps going from about 12 degrees down to about 1/2 degree. And you'll notice that, again, observing the results at this corner, that is the UVW displacements, what we get are a sudden dive for anything with an aspect ratio above 2 or 3. That is, with this slight warp in here, and any aspect ratio at all, the elements are tending to lock up, and we're getting this very rigid type of behavior. So this illustrates that the 8-noded hexahedron, that is a lower order element, is sensitive to these distortions. And when you try to represent an entire beam by so few elements, this combination of very coarse elements and some element distortion can give you some severely bad answers. The final slide in this series shows the same. We're going to use higher order elements, which happen to be tetrahedra. We've also done this with hexahedra, and it's the business of going from a low order element to a high order element, that is, having that intermediate mid-side node that tends to compensate for some of the element distortion. If you look at the figure, what you'll see again is the same problem, the same warped interface in black. The red lines are showing the outline of the tetrahedra that now compose the structure. And what you see is a much better behavior. In fact, for the U and V displacements, it's quite good out to 1,000 to 1. The W displacement, that lateral displacement, which is due to the Poisson effect, starts oscillating, but even that's pretty good out to about an aspect ratio of 80 to 1 or so. So the moral of the story here, or a generalization that we can make, is that if you, for some reason, have a distorted element set because maybe the structure is distorted, one way you get around it is go to more elements. Another way to get around it is to go to high order elements.